Hi, this is Trek, and this is the third video in my series on calculus. We're going to return to our first example with the derivative, and we're going to finish out what we talked about there. And then we're going to jump right into a ton of more examples that show some of the more complicated situations. So let's get started. Here on my screen is our example from the first video, which we never quite finished. We ended with talking about this value here. And what we were talking about was how we wanted h to approach 0. Well, now that we understand limits, or at least hopefully understand limits, we can apply that concept to this. As you can see, this is undefined at h equals 0, but it is a function that has a limit. It's continuous, assuming that both this has a limit and this has a limit. So let's go ahead and try that. So let's apply the limit at not x. Ooh, wrong one. Limit as h approaches 0 of f of x plus h minus f of x, all of that over h. So we can evaluate this. Let's try it with our function here, which is x squared. Let's plug it all in. So we'll go down a line and we'll say limit as h approaches 0 of x plus h squared minus x squared over h. Let's evaluate that. So we get x squared plus 2xh plus h squared minus x squared over h. And from here you can see easily that the x's cancel, and that's it. And we're left with this section here, which we can divide out the h, and we end up with 2x plus h, and the limit as h approaches 0. Well, now we can pretty obviously find the limit of this because there's no discontinuities or holes in it, so it's pretty easy to just plug in h equals 0 to find our final value, which is 2x. Actually, this 2x right here is what's called our derivative of the function. Now let's I'm going to clear this all away, except for I'm going to write in our value again. I'm going to write it in like this, and I'll explain this notation later. Is equal to 2x. And then I'm going to enable my function over here, f prime of x, which is what this is. This is a prime. And as you can see, it is the line 2x. We go over 1 and we go up 2. And this is our derivative of the function x squared. Congratulations, you just found your first derivative. Okay, so this is the function which tells us the slope of the line at any given point along the function x squared. So if we plug in, say, let's plug in f prime of 1 equals 2, then what that means is at 1, the slope of this line right here, like if we were to draw a this tangent line right here. Okay, come on. There we go. The slope of this line right here is 2, which it appears to be, as our scale here is, as it's pretty much it's tangent with this back of this red line here, which is our derivative, which has a slope of 2. And here we go over 1, we go over 0.5, and we go up 1, which is the slope of 2. That's approximately right. Let's try another value. So like f prime of 2 is equal to 4. So at f of 2, which is right here, we have this line right here, which looks like it would meet up right around here, which is over 0.5 and up 2, which is the slope of 4. Makes sense? Alright, great. Let's move on to our next example, which is actually a lot more simple. So let's jump over to 2x plus 1. I'm going to go through this one again, just like before. We're going to derive its derivative. So we want to know the limit as h approaches 0 of f of x, x plus h minus f of x over h. So let's derive that. Let's go ahead and get rid of that and plug things in over here. So we have 2 times x plus h plus 1 minus 2x plus 1. All of that over h, and then the limit, which I'll just shorthand right there. Evaluate this out, we get 2x plus 2h plus 1 minus 2x minus 1. Well, our 2x's cancel, our 1's cancel, and we are left with 2h, which we can divide out the h and we end up with 2. So the limit as h approaches 0 of 2 doesn't even have an h, so we can automatically assume that that is the value 2, which is true. This has a derivative of 2, so f prime, I'm going to clear. So f prime of x is equal to 2. Note that it doesn't vary as a function of x. So let's color it in here. It's a straight line. It's a constant. It has a value of 2. Note that at any point along here, we can do a rise or a run. So let's do it from like right here to right here. And it goes up 2 and over 1. That's a slope of 2. And it's the same wherever we do this. That's not how you do rise or run. And it's the same regardless of where we draw this. The slope doesn't vary as a function of x. At any given point along this function, it has the exact same slope. All right, next example. All right, so here we have an even simpler one. We have the function f of x is equal to 2. So I'm not even going to derive this one because I'd like to sort of get the intuitive sense of this one. What is the slope of the line that runs tangent to this line at any given point? Well, let's see. If we examine like this point right here, our slope is horizontal. It's just like that. If we examine right here, it's still horizontal. Over here, still horizontal. The slope of this line is 0 at all points. So let's just take a wild guess and assume that our f prime of, actually let's not put it there. Our f prime of x is equal to 0. Let's color it in, see if we got it right. Sure enough, it's just a horizontal line at 0. It's interesting that our constant function has a derivative of another constant, which is 0. Whereas before, in our previous example, we had a function that was a single order polynomial, and it also had a constant function as its derivative. Its f prime was 2. Yes, 2. Did I not? Yeah, okay. All right. Now we're gonna, before we move on to our third example, I want to talk a little bit about notation. So I'm gonna show you the second way that people like to talk about derivatives and derive them, and this will be important for talking about the various notations you'll see going forward in mathematics. So let's say we have a y final and we have a sort of y initial, and we want to know what is the value of this function. Well, it's, if y is a function of x, then it's going to be equal to y of x plus some x initial plus some change in x. I'm going to use the symbol delta here, which implies change in mathematics, minus our y of just x initial. So we evaluate our y function at an initial x value, and we evaluate it at an initial x value plus some change, and we subtract the two to get the difference in y, which is just what's right here. Well, I'm gonna substitute in some symbols here. Let's call this section here, let's call this delta y. And I've already used delta x over here, but let's go ahead and rewrite this just so it's clearer. I'm going to say y is a function of x. We're going to write it as f of x. So we're going to write f of x plus delta x minus f of x. This should start to look pretty familiar, but it'll look especially familiar once we go to the next step. I'm going to divide by the whole thing by delta x. So on this side we have delta y over delta x. And remember that delta y is the change in y over a certain domain, and x is the change in x over that same domain. So they have a relationship with each other. So what we have on the right side here is f of x plus delta x minus f of x, all of that over delta x. And what we want to know is, and we want to evaluate this as delta x, the change in x, goes to 0. This is the exact same thing as the derivative. This is what we're doing here. We want to know what the ratio is between the change in y to the change in x as this function goes over delta x equals 0, goes towards delta x equals 0. So I'm going to introduce something called a differential, and they look like this: dy over dx. So this is differential y, differential x. A differential just means infinitesimally small. Now, differentials are concepts, a lot like infinity. They aren't numbers. You can't say like 3 times dy, and that's never going to be the solution to a problem. It's kind of like saying 3 times infinity, which also isn't a number. They are concepts. However, their ratio is numerically significant. For example, actually, before we talk about that particular differential, let's say, like, what is the limit as x approaches infinity of x over x? Now, obviously, we could just divide this out and get 1, but I think it's important to think about what's actually happening as x goes to infinity. We get, on the top we get, and you should never ever write this because it'll get you smacked around by math communities, but we get infinity over infinity, right? Well, infinity isn't a number, and you can't divide a number, and so this isn't, like, infinity isn't a number. But their ratio is significant because they're consistent with each other. They're constrained by this function here. They always have the same ratio. We might not know what their value is, but their ratio is the value 1. Differentials are the same way. So dy is not a number. It's an infinitesimally small concept representing a change in y. And dx is also not a number. It is an infinitesimally small change in x. But their ratio is constrained by this function here. This one right here. F of x plus delta x minus f of x over delta x. And this is the limit as delta x goes to 0 of delta y over delta x. So these three things are equivalent. Oh, except this needs this needs a limit as delta x goes to 0, which I'll just put quotes there. So this is another notation you'll see a lot. I'm going to clear this. So when we are asked about the derivative of a function, say we have y equals, oh, sorry, I accidentally changed my size. y equals 5x plus 3. If asked the derivative, you might say that dy dx is equal to whatever the derivative is, which I'm just going to tell you what it is, but we'll explain it later, which is equal to 5. And what this means is the rate of change at infinitesimally small changes in x and infinitesimally small changes in y always has the ratio of 5. And it's important also to understand what the role of these variables are here. This means the derivative of the function y with respect to x. If, for example, we had y equals 5x plus 3z, dy dx is still equal to 5, because you can only take derivatives with respect to one variable at a time. Our function y is not changing. Our function y with respect to x is not changing as z changes. It's only changing as x changes. So this 3z is essentially what is a constant with respect to x. And you'll see this a lot as we go on, but it's important to understand that this right here is talking about the relationship between the function y and changes in x. And as I showed you earlier, I will use the notation that looks like this quite a lot, which this just means this is the same thing as our function, which might have any variable, but we'll just say it's y. This is the same thing as dy dx. So this is saying the derivative with respect to x. Okay, so now we can move on to our next example. You won't see me use the dy dx syntax a whole lot, just because my example program here doesn't support it. I'm mostly going to be using this language here, f prime of x. But when we get into a lot more of the examples where I don't really want to use a graph, I'll try to use dy dx a lot, because it is very important, and it is sort of the proper syntax and notation for some of the more advanced processes you'll use later on. So get used to it. Don't just ignore it. All right, so I want to go through some examples where we derive. So I have one here. This is ax. This is my function here. So we have f of x is equal to ax squared plus bx minus c. And we want to find the derivative of this function. I'm going to go ahead and turn it on real quick just so we can talk about what it looks like. So it is a paraboloid. I just set our a, b's, and c's to some random values at the moment just so it's ended up on screen. But yeah, this is how it looks like. So let's just talk about some quick sort of snapshot values to get an idea of what this graph is going to look like of its derivative. So we got a really high value here. So around 6, we got, what does it look like? Like, I don't know, 8 or so. It looks like it has a horizontal line around 3. So we're thinking that there should be a horizontal line at around 3. Or, sorry, a derivative should have a value of 0, because the slope of the line is 0. Likewise, it looks it's symmetric. It's a paraboloid, so we're going to have some negative value here. So we're going to have negative values, 0, and a symmetric positive values on this side. And we're going to flip over 3. So let's go ahead and derive it and see what actually ends up coming out. So we want to take the limit as h goes to 0 of a x plus h squared plus b x plus h minus c, all of that minus a x squared plus bx. It's plus, no, it is minus c. Okay, minus c. All of that over h. So let's start multiplying this out. We get ax squared, I'm just going to put quotes here, plus 2axh plus ah squared plus bx plus bh minus ax squared minus bx plus c. I forgot this c right here. There's also a minus c. All of that over h. That's big and long, but I think a lot of this cancels out. For example, we have, that should be squared. So this cancels out, because we have another one here. We have, this bx cancels out. Oops. These c's cancel out. And we are left with, go back to black, 2axh plus ah squared plus bh over h. We can divide h out because all of our terms have h on, and we end up with 2ax plus ah plus b. And we can take our limit now. We just plug in h equals 0 because this is pretty clearly something that doesn't have any discontinuities or any sort of doubts as to whether or not it's just, you know, a line that continues on without any sort of indeterminacy. So we're going to plug in h equals 0. So that'll make that disappear, and we end up with 2ax plus b. So notice that c didn't even end up in our derivative, and this is, by the way, the correct derivative. We don't need that anymore. So our f prime of x is equal to 2ax plus b. I'm going to clear it and write it again so we can talk about it when it's on our screen. F prime of x is equal to 2ax plus b. Alright, so before I graph this, let's talk about what we mentioned earlier, which is that on this side of 3 it should be negative, on this side of 3 it should be positive, and we should reach the value 0 right at 3. And let's plug in our numbers here so we can figure out stuff better. The a is just 1, so we get 2x minus 6. Well, let's plug in 3, for example. If we plug in 3, we get 0. So f prime of 3 is equal to 0, which makes sense. We said that it was 0 at 3. F prime of, so let's say, 2 is equal to negative 2. It's negative before that. And f prime of 4 is equal to 2, which it's positive on the right side, and it's symmetric. Let's go ahead and graph it. Which, this looks about right. I mean, at 3, we have a value of 0. At 2, we have a value of negative 2. And at 4, we have a value of 2. This line right here represents the slope of this curve here. Perfect. All right, let's jump to the next example. Okay. I'm trying to get don't look at that. I'm trying to get these last couple of examples are going to be more complicated to try to show you like how complicated this can get. They aren't like super complicated or anything like that, but we're going to work through them because I think that they're interesting. So our function this time is f of x is equal to the square root of ax. And in this case, I'm just using the example of a is equal to 2.5, but we can change that and I can show you what the graph looks like. So we want to know the limit as h approaches 0 of the square root of a times x plus h minus the square root of ax, all of that over h. Alright, so I'm going to use something called a conjugate here, which I'm not sure when they're supposed to be first introduced to you. You might have already seen them already, but the conjugate is just sort of an algebraic tool, sort of like partial fraction decomposition or something like that, that helps you deal with roots. And how it works is the conjugate of any two terms, like for example these two, is simply the same exact terms, except you change the symbol in the middle. So our conjugate in this case is square root of ax plus h plus square root of ax. And I'm going to multiply it by that over itself. Square root of x plus h. We'll talk about conjugates more when we get into the complex numbers. Plus square root of ax. So this has a value of 1, so we can multiply it through. And what happens when we multiply the top is we get this. So let's we get ax plus h. Let's see. Plus, I'm going to call, I'll write it out, it's fine. Square root of ax plus h times the square root of ax minus square root of ax plus h times the square root of ax minus ax. So this is the first two terms multiplied together, this one and this one. This is the first and second, as in this one and this one. This one is the second and the first, this one and this one, and this is the second and second. So this one and this one. Well, the useful thing about conjugates is they always have a pair of canceling terms. Right here. This cancels out and this cancels out. I'm going to turn this off just for while we're working. And this is why it's useful for dealing with roots, is notice our last two terms are squared, and our terms that still had roots in them are canceling each other out. So we end up with, wrong color. The limit as h goes to 0 of ax plus h minus ax, all of that over h times square root of x plus h plus square root of ax. Alright, I'm going to factor out our a's and our h. So we end up with quotes a over h, x plus h over square root of a x plus h plus square root of ax. So this is now, now we multiply this through, wait, what did I do wrong? I got to turn this wrong here. One second, check my notes. Oh, okay. I got it. Alright, sorry, I know what I did wrong. Or didn't realize. Minus x. That's what I was thrown off by. So, because I forgot to include this term here, because this is also getting factored out and there's a minus x there. So, this x and this x will cancel out. And then we'll just have h on the top and be able to cancel out this h and that h. So we end up with the limit as h approaches 0 of a over square root of ax plus h plus square root of ax. And now this is safe to plug in 0 for h. And we can take our limit. So we plug in 0 for h. This is an a. And we get a over square root of ax plus square root of ax. So that's equal to a over 2 times the square root of ax. And if you recall, square root of ax is actually our function. So I'm going to clear all that out and write it again. So our f of x is equal to square root of ax, and our f prime of x is equal to 2 over a. Is that right? No, it's a over 2. A over 2 square root a of x. And it's in the denominator now, so it's actually square root of ax. All right. Well, that went only slightly poorly. Let's take a look at some of the function values. Okay, so here's our actual function. It is asymptotic as well, it's not asymptotic. Never mind. So we got a value going off here. I'm using a equals 2.5, so it's the usual square root curve. Just kind of goes off this way. Let's take a look at some of the important values. Notice that at x equals 0, we have it approaching a vertical line, and that means our slope needs to be near infinity. If you notice, our f prime of x, as x approaches 0, our denominator goes to 0, and our function value, our derivative function value, approaches infinity. But the square root function is interesting in that as it goes off far, infinitely to the right, our function approaches a horizontal line. The further you go to the right, the more diminishing returns you get, and it eventually becomes basically horizontal. It approaches horizontalness. So way off in the distance, we have a horizontal line. And notice that as x becomes huge, our number here approaches 0. Now let's just pick some middle values to talk about. 4, so it should be, what is that? That's roughly like that. That's got a slope of, that's 2. So these are in units of 0.5, so that's 0.5. And this is 1, and this is 2. So we got a slope of 1/4 right here. Well, let's plug it in. We'll plug in 4 and 2.5, so we get 10, square root of 10 here, and 2.5 over 2. That's 10. Let me bring up the calculator real quick. So 2.5 divided by 2, and divided by the square root of 10, which is about 3.3. It's a little bit more, but it's close. I'm probably just off on my graph here, but we can actually calculate that later on if we need to. But that's the idea. Let's go ahead and put our graph out, see what it looks like. So as x becomes closer to 0, notice our value goes off into infinity, just like we discussed. And as it goes way to the far to the right here, which I'm going to bring this way, notice that it eventually goes to 0, as in a slope of 0, or a horizontal line. Alright, let's go move on to our final example. Alright, so our function is a over x and this function goes to 0 as x approaches infinity to the right, the infinity over here. As x goes this way, our function goes to 0 because we get an absurdly large number over a divided by an absurdly large number that is dramatically larger than. So that goes to 0. On the other side, we get negative x, which is the exact opposite. It's just negative infinity. And as x approaches 0, we get a over 0 and a over negative 0, essentially. And when I say 0, I mean an infinitesimally close number to 0, because we're talking about limits here. Its derivative, if you see, it approaches a horizontal line as you get way far out. So we should have a value of 0 in the distant far right, infinitely into the far right. And likewise on the opposite side, we get 0 on the far left. And as we come in from the left, we should have a negative value, negative, negative, more and more negative, all the way to a negative infinity value of our derivative, because the slope is almost vertical. It'll eventually just go straight to vertical. So we have horizontal slopes out way far out distant this way. And likewise here, we still have a negative slope, oops, because we're going from left to right. So our function is always decreasing as far as slopes are concerned. All the slopes are negative. So we have 0, slightly negative, more negative, more and more negative, infinitely negative, less negative, 0. So our derivative should look something like, I'm going to clear this, something like this. So we start out at 0, we become negative, 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 infinitely negative, and then we come back up to 0. But we're always underneath the plane here, underneath the line here. All right, let's move on to the derivation. F of x is equal to a over x, and we want to know f prime of x, which is equal to the limit as h approaches 0 of a over x plus h minus a over x over h. To get rid of this, I'm going to multiply by our missing denominators here to get like values. So over here I'm going to multiply by x plus h over x plus h. And over here I'm going to multiply by x over x. And that will give us, I'm just going to quote our limit here, that will give us ax over x times x plus h minus ax plus ah over x times x plus h, all of that over h. Now we can combine them, and as you can see, our ax's cancel, and we end up with a negative ah. Yeah, that's right. So we got our limit. We end up with negative ah over x times x plus h, all of that over h. Well, we can factor out this h and then divide it into here, so we end up with the limit as negative a over x times x plus h. And this is now safe to plug in 0 for our h, since it no longer creates a discontinuity. It's no longer a hull, since we can just kill this h right here. And we end up with negative a over x squared. All right, so let's jump back to the beginning. So we have f of x is equal to a over x, and our f prime of x is equal to negative a over 2 over x squared. All right, let's talk about how this fits into what we described earlier as sort of our idea for what the function should look like. Remember that our slope approaches 0 as we go off into infinity, which it does. So as x is equal to, say, 100, we get a value that's very small. It's a over 100 squared, negative a over 100 squared, which it is a very slightly negative slope. And notice that our the height of our value is right, the most negative of our value is right up. As x approaches 0, our slope is the most negative, which, as you can see, it goes to negative infinity. Because as x approaches 0, we get negative a over a very infinitesimally small 0, which is negative 2 over an extremely small value, which is negative infinity. And likewise on the other side, as x approaches 0 from the left, so we get like negative 1 squared, we also have a negative slope. So it's very much similar to right here. In fact, if you notice, we have negative slopes throughout because our x squared washes out all the negative values. And as we go off to the left towards the negative infinity on the x-coordinate system, we also get a incredibly small value that eventually goes to 0 as our limit. But it is a very slightly negative slope. It eventually becomes 0, a horizontal line. In both directions, horizontal line. At zeros, we get vertical lines. Let's turn it on, see how it looks. So, like I said, as x approaches 0, we get negative infinity on both sides, infinity, and as x goes way out, we approach 0 on both sides. Fair enough. All right, thank you, everyone. That was it for introductory concepts to the derivative. We are now going to move on to what I call the shortcuts unit, where we learn how to do all this in way less steps. We're going to cover power rules and things like that, chain rule, and all the different tricks to getting the derivative faster and easier than having to put it through our formula. So I'll see you in the next video. If you enjoyed this, then like and subscribe. Thanks. Bye.